Okay, this is the section 8.3 notes for the online trig class, Trigonometric Equations. Solving equations is a technique that has been used in early algebra classes. Solving 2x plus 1 equals 7, you would subtract 1, divide by 2, and get that x equals 6, and that's the only solution that works. So we can also solve trig equations, but the problem is that there are going to be multiple answers that could make a statement true. So we have to be careful, first of all, following our directions to make sure that we are looking for our solutions in the right subset. And what I mean by that is it just from 0 to 2 pi, or are we going around and around the circle as many times as we want? So determine whether the following values of theta are solutions to the equation sine theta equals 1/2. So this first problem is asking us to just look at this and say, do these things plug in correctly? So if we write sine of pi over 4 equals 1/2, and we ask, is that actually equal? Well, if you remember on your unit circle, pi over 4 is the 45 degrees, and that ended up being square root of 2 over 2, square root of 2 over 2. So this is square root of 2 over 2, which does not equal 1/2. So therefore, this is not a solution to the following equation. If we put sine of pi over 6 in, we ask, is that equal to 1/2? So again, think about your unit circle. Pi over 6 is related to 30 degrees. And remember, that would be 30 is the reference, and this would be 60. So that's 1, 2, and square root of 3. So yes, sine here is opposite over hypotenuse, so it is 1/2. And again, if you have your unit circle memorized, which you should get memorized, especially for this first, well, pretty much for any test in this class, but this is definitely equal to this. So this is a solution to that equation. So because all of the trigonometric functions are periodic, which means they repeat a pattern over and over again for a certain amount of degrees or radians, this means there's actually an infinite number of solutions to that equation. So let's think, what would be some other ones? Well, if you think about just within 0 to 2 pi, so here was that triangle, 30, 60, 90. This is 1, 2, and square root of 3. This is all science teachers are crazy. All means that every trig function is positive. Sine would mean that sine is positive. So that means there is actually another triangle over here with the same reference angle where the opposite would still be 1. This would be negative square root of 3, and this would be 2, but the sine here is still 1/2. So this is 180 minus 30, or 150 degrees is another place that happens. Remember, we would want that as radians, since our answer is in radians. So other radians that would work, if this is pi over 6, 2 pi over 6 would be 3 pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. 5 pi over 6 would be this one right here. So 5 pi over 6. So then you've got to realize that down here in the quadrants 3 and 4, this would no longer be true because you would have negative ones for your short side of your triangle. So these are the only two answers, pi over 6 and 5 pi over 6, if you only do one revolution. But we could do another revolution of our answer. So we could do pi over 6 plus 2 pi. That means we go around a whole time, and we would get a common denominator there. So that would be 12 pi over 6. So another solution would be 13 pi over 6. So there's another solution. There's another solution. We could also do a revolution around the 5 pi over 6. So 2 pi over 1. So that's 5 pi over 6 plus 12 pi over 6 if we get a common denominator. So that's 17 pi over 6. And on and on. We could keep adding or subtracting 2 pi as much as we want. For example, we could have just as easily subtracted 2 pi. Now that'll give us a negative radian, but it's still an angle that would end at the same location. Those, remember, are called coterminal angles. So negative 11 pi over 6 would be another one. So just pretty much, if you find one solution, adding multiples of 2 pi will give you a whole bunch more solutions that are coterminal, which means that they have the same triangle attached in that same quadrant. Okay, so let's look at another example. So this says we want to solve the equation involving a single trig function. So find all the solutions. That means we will go around the circle as many times as we can, infinitely. And this is our equation. So we need to solve the equation for theta when, okay, so for this first piece, we're going to just go between 0 and 2 pi. And you usually start that way because what I did, remember, a minute ago was I found those first two answers that were in quadrants 1, 2, and 3, and 4, depending on what sign we were dealing with, which we were dealing with a positive 1/2 before in that last example. Then we say, okay, you can keep going around the circle either forwards or backwards and end at that same location. So essentially we were adding and subtracting 2 pi to get other solutions. So first of all, let's focus on just from 0 to 2 pi. So we take this equation and we solve it for cosine. First we would add over the square root of 3 and then divide by 2. And notice that is going to relate back to that same triangle we were just looking at a minute ago. So if we look back in quadrant 1 here, if it was a 30-degree reference angle and a 60-degree up here, this member is across from 30 is 1, across from 60 is square root of 3, and 2 is the hypotenuse. That's our 30, 60, 90 triangle. So adjacent here is square root of 3, and hypotenuse is 2. So this is actually correct. This is giving me square root of 3 over 2. So theta in this scenario, one of the answers is the same guy we just got back here, which was pi over 6. Now remember, all science teachers are crazy tells me that when we're dealing with cosine, we don't want to be in quadrant 2 to have another positive. We want to be down here in quadrant 4. So this is also a 30-degree reference angle. This is -1 here, and this is 2, but still adjacent is square root of 3, and hypotenuse is 2. So this is the angle 11 pi over 6. So between 0 and 2 pi, these are the two solutions. Okay, this is just from 0 to 2 pi. Those are the two quadrants where we get positive cosine values that are square root of 3 over 2. So now we want a general formula for all the solutions. Well, we're going to take the answer we got, and the way we write this is we say we're going to add 2 pi multiples, so that k is standing for an integer. So either 2 or 4 or -1, -2. It's just telling us either add so many times around or subtract so many times around. So that would be one solution, and that is an infinite number of solutions because integers go on forever. Theta 2 would be the same scenario except you start with the 11 pi over 6, since it is actually a different location. And that would be that. List 8 of the solutions. Okay, so this just means we're going to run through some. So let's do pi over 6 plus 2 pi times 1. So if k equals 1, this we did a minute ago. This is pi over 6 plus 12 pi over 6, which equals 13 pi over 6. So there's one solution. If 11 pi over 6 is added to 2 pi times 1, that gives me 11 pi over 6 plus 12 pi over 6, which equals 23 pi over 6. There's another one. If k equals -1, we can get two solutions from both of those. So pi over 6 plus 2 pi times -1. That would be pi over 6 minus 12 pi over 6. So that would be -11 pi over 6. Or we could also do 11 pi over 6 plus 2 pi times negative 1. So that's 11 pi over 6 minus 12 pi over 6, which equals negative pi over 6. We can find 4 more. If we add 2 pi, so I'm just going to do this right here. So if k is 2, so pi over 6 plus 2 pi times 2, that would be pi over 6 plus 4 pi, which equals pi over 6 plus 24 pi over 6. That would be 25 pi over 6. And then we would need to do positive 2 in the other case. So 11 pi over 6 plus 24 pi over 6. That would equal 35 pi over 6. And then just to finish this off and get 2 more rounds. So see, we could do this forever. We could let it be negative 2 for k. So pi over 6 minus, because it's going to come out to the same 24 over 6 if it's a 2 times 2 pi. But this time we're subtracting, so negative 23 pi over 6 and pi over 6, 11 pi over 6, excuse me, minus 24 pi over 6. That would be negative 13 pi over 6. So you start to see sort of a pattern in how they work out. But this would go on forever. We could keep doing this and building solutions. So actually the general format is better if you're trying to give me multiple solutions, more than just from 0 to 2 pi. Okay, so we're going to solve equations involving single trigonometric functions again. So solve the equation sine of 3 theta equals negative 1. Notice something in this problem. You have an extra thing inside there with theta. This is where substitution is going to play in a minute. So when does the sine function equal negative 1? So think about your unit circle. Sine, remember, is the y value when we're on the unit circle. So when is that negative 1? Well, that's down here. This would be 0, negative 1. That's 3 pi over 2. Because of sine being a period function, in other words, it repeats a pattern from 0 to 2 pi, we can write all of the solutions, the general formula, as 3 theta equals 3 pi over 2 plus 2 pi k. To get theta, we need to divide everything by 3. So 3 theta equals 3 pi over 2 plus 2 pi k. We're going to divide everything by 3, even this stuff over here, trying to solve it for theta. Now, in this scenario, that's going to be 3 pi over 6, because 3 pi over 2 divided by 3 over 1, you multiply by the reciprocal of the bottom to get rid of that. So that's, in fact, you can actually see that the 3's cancel when you do it that way. So this ends up being theta equals pi over 2, once we reduce that down, plus 2 pi k with a 3 in the bottom there. So you can leave the k on top or you can pull it out to the side. So this would be my general formula. And in this scenario, this is the only place that sine can equal negative 1. Because remember, sine is the y value, and the only time on the unit circle we equal negative 1 for y is down here. So over the interval from 0 to 2 pi, the solutions were just 3 pi over 2. And that's because it is the only location where sine, actually let me back up, that may not physically be true. Let's plug in a couple examples and see. Because if it was sine theta, yes, that would be the only solution, but we do have that 3. So let's check what happens if we put in a 1 for k. So pi over 2 plus 2 pi over 3 times 1. We need to get a common denominator. So this would be 3 pi over 6 plus 4 pi over 6. That is 7 pi over 6. And that actually is between 0 to 2 pi. See, it's always good to check. So we know that if we plug in 0, 2, I didn't do 0. Okay, so if you plug in 0, pi over 2 is a solution. If you plug in positive 1, 7 pi over 6 is a solution. And I know that's between 0 and 2 pi because to be smaller than that, 12 pi over 6 is 2 pi, so this is smaller. Let's plug in 2. So pi over 2 plus 2 pi over 3 times 2. That would be pi over 2 plus 4 pi over 3, which if we get a common denominator, that would be 3 pi over 6 plus, multiply this by 2, 8 pi over 6. That's 11 pi over 6. And that is still smaller than what we had there. So I did the 0 case, I did 1, I did 2. Let's make sure that negative 1 doesn't also give us something between 0 to 2 pi. Because if we go one more step with these, you're already at 11 pi over 6. You're going to jump up too high and you're going to be bigger than 12 pi over 6, which means you wouldn't be between 0 and 2 pi. But if this was a negative 1, let's just make sure it doesn't give us anything that we should be concerned about. So this would be pi over 2 minus 2 pi over 3. Multiply by 3 on this side, 2 on this side. That's 3 pi over 6 again, minus 4 pi over 6. So see, that's negative pi over 6. That's no longer from 0 to 2 pi. It's the other direction. So it looks like these are our 3 solutions here. And if you were to draw those out, you'd have pi over 2 is up here, 11 pi over 6 is down here, and 7 pi over 6, if you think about on the unit circle, trying to draw that in there. So yeah, here's like 11 pi over 6. And 7 pi over 6 is actually over here. So you see it kind of splits the circle into 3 chunks, 3 theta, okay? All right, so we're going to try another one. This one says use a calculator to solve. Sine theta equals 0.4 when theta is between 0 and 2 pi. So let's read what we should do here. So it says before a calculator is used, what quadrant should we expect to find theta? Okay, so when is sine positive? Remember, all science teachers are crazy. So in these top 2 quadrants is when sine is positive. So all of these up here is when sine is positive. But if you remember how to solve this, you need to do the inverse of both sides. Because of that, the calculator is only going to give you this piece of information, and I'm going to explain why. When you have to use your inverse, remember you have to do your restricted domains. So that's negative pi over 2 to pi over 2. So because the calculator has this restricted domain for inverse of sine, and because sine is positive only in these 2, when you plug it into your calculator, you're only going to get this quadrant right here. So let's write that down. So I didn't answer this one yet. This was supposed to be 1 and 2. That's where sine is positive. So to get theta by itself, we take the inverse of both sides to get theta equals sine inverse of 0.4. Make sure we're in radian modes, and we're going to get the answer to that. So 0.4, make sure you're in radians. Inverse sine 0.41, so 0.41. So draw a sketch of the location of this angle on a graph. is this one of the quadrants we expected? So if you think about what pi over 2 is, because if you don't know where these fall, you can just think of the quadrants and figure out those. Pi divided by 2 is 1.57. That means this is 1.57 up here. This is 0. So 0.41 is somewhere around here. So that is 0.41 as radians. And yes, this is the quadrant that I expected it in. So recall from previous sections that because sine has to be 1 to 1, the domain was the negative pi over 2 to pi over 2. So the answer the calculator gives is in this interval. The other solution to this equation when theta is between 0 to 2 pi is when we're over here, because this is the other place that sine could be positive. So there's going to be another angle over here that has a reference angle of 0.41. So to figure out what that is in radians, we have to know what pi is. Well, pi is 3.14. So if we take 3.14 and subtract off that reference angle, that'll tell me how far this is from 0, because we're trying to figure out if this is 3.14, how much did we measure over from the 0 position. So if we subtract, we get 2.73, which I got that from 3.14 minus the 0.41. So that is my other possibility in radians on the unit circle from essentially from 0 to 2 pi. Okay, moving on. So we're going to be solving another equation, except this time this is kind of what I was trying to prep you for in the last set of notes. This is quadratic looking, so we're going to use a substitution to make this easier to work with. We let cosine theta be u. So if you have cosine squared, that would be 2u squared minus u minus 1 equals 0. So now we've got this in what looks like just a regular old quadratic. We can factor this, because this does factor. If you haven't factored in a while, you can either try trial and error, or you can try something called factor by grouping. Factor by grouping is when you multiply the first term times the last term, and you list all the factors, and you figure out, after you've listed all the factors, which is only one pair, you ask yourself the question, if this has to multiply to -2, what would need to happen so that it adds to -1? So and it has to still multiply to -2, so it has to be different signs, and the negative needs to go with the 2. Then you take that and you split this middle into 2 pieces, and it doesn't matter which one you write first. You then pull out a GCF by factor by grouping, and we have to pull something out, so I'm going to pull out a 1. And then we set the u minus 1 is one parentheses, and the parts in front are the other parentheses. And then we set each equal to 0. So this is positive 1. That's a horrible 1. Hang on. So positive 1 is one of the possibilities, and this is -1/2, because we would subtract that over and then divide by 2. Now, remember, those are not the answers to the final part of this equation. Essentially, we solved the substituted part. So we have to turn these back into cosines. So cosine theta equals 1, or cosine theta equals -1/2. Now, that means that we have 2 different sets of solutions to solve. So if you think about what it would look like on the unit circle, cosine being 1 is going to mean when is the x1 on this all the way around. That only happens right here. Okay, any other time you don't have a 1 for the x spot. You have a -1 over here, but not a 1. So one of the thetas would be 0, because notice this says you can equal 0 but not 2 pi. That just means you stop before you get to the very end so that you don't count this angle twice. -1/2's a little different. So this is when cosine theta equals 1. So for cosine theta equals -1/2, First of all, we have to know which quadrants is cosine negative in, so all science teachers are crazy. Cosine is negative over here in quadrants 2 and 3. So I'm going to highlight that. And then we need to talk about what angle would give me a cosine of negative 1/2. So draw just a reference angle here. And remember, cosine is adjacent over hypotenuse. So that means this is a 30, 60, 90 again, with this angle being 30, because 30 is always across from 1, so that's the square root of 3. So that means that this theta is a 60-degree reference angle, or another way of thinking that is 120 degrees from 0, because this has to add up to 180. So 120 degrees is, if we multiply that by pi over 180, those are both divisible by, first of all, the zeros cancel out, but they're both divisible by 6, and that would be 2 pi over 3. So 2 pi over 3 is one of our solutions. And then there's another match down here, because we just said that there's 2 possible solutions where cosine could equal negative 1/2. So this one is 180 plus the 60-degree reference angle. So that's 240 degrees. And 240 times pi over 180, that is both divisible by 6. So that would be 4 pi over 3. You could have just counted that, but that's the nice thing about the triangles. You can always figure things out from them, even if you don't have it memorized. So these are the 3 solutions between 0 and 2 pi. And if this had not been a 1, there possibly could have been 4 solutions, but because cosine theta equals 1, that's very specifically a singular point where that happens. Okay, example 3 says solve the equation cosine squared minus sine squared plus sine theta. So cosine squared theta minus sine squared theta plus sine theta equals 1. It says to solve an equation, all the trig functions should be the same. So let's use an identity to rewrite the equation in terms of all sines or all cosines. So this is going to be a little bit tricky. So let's try to think through what we could do. Okay, so when I look at one of these problems, I try to get rid of the one that's the easiest to get rid of, which if you have 2 of something, it's usually harder to get rid of it than if you just have 1 of something. Also, anytime you see sine squared or cosine squared, first of all, if they don't already have a plus between them, you can't use Pythagorean theorem in that way, the identity, but you can think of sine squared theta plus cosine squared theta equals 1. You could solve this 2 different ways. You could solve it for sine squared by subtracting over cosine, or you could solve for cosine squared theta by subtracting over sine. And that's the case I'm going to use for this, because I want to try to get rid of this cosine squared. So if I change that to 1 minus sine squared theta, and then bring everything else down, we'll see that we now have 1 minus 2 sine squared thetas plus sine theta equals 1. We can subtract the 1 over. And that gives us 0. And then I would factor out a sine squared, or excuse me, a sine theta, not a sine squared, because they both don't have squared. That would leave me with negative 2 sine theta plus 1. And then I could set each of those equal to 0 using the factor theorem. So one possibility is going to be sine theta equals 0. The other one, we will subtract over negative 1 and then divide by negative 2. So it's actually 1/2. So we're trying to solve both of those. So I have sine theta equals 0 and sine theta equals 1/2. So if we think about when is sine 0, remember sine is the y value, that happens in 2 locations on our unit circle. So this is going to happen at 0 and at pi if we're in radians. So theta would be 0 and pi if we're only between 0 and 2 pi, which we are. So there's one set. Sine theta equals 1/2. First of all, sine is positive in quadrants 1 and 2. So it's going to be 2 solutions from those 2 quadrants. And 1/2, remember, related back to opposite over hypotenuse. So this was the 30, 60, 90. So 30, 60, 90 in this place where the 30 degrees is your reference angle is pi over 6. And then over here we have that match, which is also 30 degrees. And remember, this is pi over 6. 2 pi over 6 is pi over 3. 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. And 5 pi over 6. So those are my solutions for the 2 separate equations we got after factoring. You have to be careful. In some cases, the techniques that we just used will not help us solve trig equations. In that case, a graphing utility will be the best way to do it. So I want to show you this real quick. This is our last example. It says solve the equation 3 cosine x plus x. So that's one side of the equation, equals 4. So you treat this as 2 separate equations. The only time they're equal to each other is their intersection. So 2 separate equations will be equal to each other at the intersection on the graph. Okay, so I went ahead and pulled up Desmos, and I did this already, so let me find it. There we go. So if you notice on my picture here, I put in y equals 3 cosine x plus x. That represented the left side. That gave me this weird sine wave that's kind of climbing up a hill. And then I put y equals 4 because that was the right side of the equation. Notice that those 2 lines overlap at a singular point. This is going to be our point of intersection. So 4.534 and 4. So let's type that in on our notes. So 4.534 and 4. Since the original equation was trying to solve for x, then all we care about is the x. So it would be approximately 4.534. So kind of interesting that you can use the graphing utility that way. You guys don't have access to that for the exam, so it's not something I would lean on as a crutch, but it is interesting to see how the answers to these are really related to the graphs. So that is it for this section.